Okay, it's Brian here. We're going to continue to talk about chapters 4 and 5. We're going to continue to talk about force and motion, remind you of a couple of the key details, but we're ready to dig in and do some problems. And let's think about this one. So here's my first situation. A 60-kilogram person stands on a bathroom scale in an elevator. Now, why would you be standing on a bathroom scale in an elevator? We're not going to talk about that. And it's accelerating upward at 1 meter per second squared. Question, what is the reading on the scale? That's what we need to think about. Now, how do we solve this problem? And I want to mention this. When I look at a problem, I don't like know how to solve it. I think about my dog Pumbaa. And when Pumbaa and I would go hiking and we would come to a river, he didn't have a plan. It was like, I don't know how, I don't know. I just know I need to be on the other side of the river. So he had his procedure, and his procedure for getting across the river was basically this: 1, jump in, and 2, don't drown. And that's what he would do. He just he doesn't know what he's going to do. He just kind of jumps in, and then he just starts swimming, and then does what it takes to not drown. And at a certain point, he gets to the opposite side of the river. He would just dive right in. And when you see a problem, I don't want you to worry about you don't know how to solve it, and don't say to me, what equation do I use? Don't ever say that. That is a terrible thing to say to me. Don't say what equation. Okay, don't say that. What you're going to do is just start off and think about the procedure. What is the procedure that we do? And for these force and motion problems, it's always exactly the same. We have 2 steps to our procedure. The first one is to draw a motion diagram, and 2 is to draw a free body diagram. And I want you to do every single problem this way. Draw a motion diagram, draw a free body diagram. Just do it. And it kind of helps you wrap your mind around the problem and think about physically what's happening. Well, the elevator is accelerating upward at 1 meter per second squared. Okay? So that means that the dots are getting farther apart. The velocity vectors are getting bigger. Net result, there is an acceleration, and the acceleration is directed upward. Now, since the acceleration is directed upward, that tells me that the net force is directed upward. Well, if the net force is directed upward, that lets me make my free body diagram quantitatively accurate. And if someone is sitting on a scale in an elevator, the scale exerts an upward normal force on the person, and that's what the scale reading is. The scale reading is the normal force in newtons. But there's also a downward weight force acting on the person, but the weight force is smaller than the normal force because I know the net force is directed upward. Because the next piece of the puzzle was actually asking us to do this, which was just to say, now the next piece of the puzzle is to write down an expression for the net force in terms of the forces in the diagram. And this is a piece where a lot of people have some difficulties. This is not trivial. This is, in some cases, the hardest part of the problem. So check it out. Upward normal force, downward weight force. F net is equal to the force in the positive direction, N, minus the force in the negative direction, W. Okay, so that's an expression for the net force in terms of the forces in the diagram. Now the next piece of the puzzle asks us to solve for N. And it says this is the scale reading. It's kind of like reminding us of this fact. So remember, we said the acceleration is directed upward. The dots are getting farther apart. The velocity vectors are getting bigger. The acceleration is directed upward. And it's directed upward, and we know it's also 1.0 meters per second squared. When we wrote down the free body diagram, like so, we had a normal force upward, we had a weight force which was acting downward, and we had an expression that said that F net was equal to N minus W. We can rewrite this equation and say that the normal force is equal to F net plus W. And now we're at a point where we can use an equation, because we can say F net, that's just equal to m times a. That's Newton's second law. We can always use that. So rewrite my expression and say the normal force, which is what I'm looking for, is equal to m times a plus w. But I'll rewrite w as m times g. Perfect. Now you'll note I have not used a single number to this point. I have not used a single number to this point, but I've gotten to this point, And I've got an expression that I can use to solve for n because I know the mass, I know the acceleration, and I know the acceleration of gravity. So I am good to go and I can complete my solution. And if we do that, okay, we end up with a force that's 650 newtons. We end up with a force that's 650 newtons. And of course, the next piece is we want to assess, is this reasonable? And the answer is yeah, because if you're in an elevator and the elevator is accelerating upward, there's an upward acceleration, okay? You feel heavy. You feel heavy. You know this experience. And feeling heavy just means the normal force on you is bigger than your weight force. And the weight force is about 600 newtons or so for this particular person. And so the normal force is bigger than that. And bigger than W, the person is going to feel heavy. Because remember, that normal force, that is the apparent weight. And that's something that we expect you to have picked up from the chapter. Because remember, scales measure a normal force, not your weight. So the reading on the scale isn't your weight, it's the normal force. And the normal force is actually what you perceive as weight. Like right now, you don't feel your weight. There's the weight force of gravity, which is pulling you towards the center of the earth. You don't feel that. What you feel is your chair pushing up on you or the floor pushing up on you. The magnitude of the supporting contact forces, that is your apparent weight. That is your apparent weight. And so if the N that we measure, the normal force, is bigger than W, the person's apparent weight is bigger than their actual weight. And so the person feels heavy. And so our assessment is the situation works out exactly as we know that it does. Now it seems weird to think that the apparent weight, the weight that you feel, is just equal to the normal force. Because you think, don't you feel your weight? You don't. Think about this. If the only force that's acting is weight, okay, we know what that means. That means the acceleration is the free fall acceleration. You are in free fall. And if you're in a situation of free fall, what you experience is weightlessness. And we will see examples of this. The people who are in orbit around the Earth on the International Space Station are being acted on by the weight force. That's what keeps them in orbit. But they feel weightless. They are actually in free fall. They are not weightless, but they don't feel the weight because the apparent weight, what you actually feel, is just equal to the normal force. And if you are in free fall, the normal force is equal to 0. And so you feel weightless. And we have a great video that I'm going to show in class where we made this little free fall box in the Little Shop of Physics, and it's super awesome and it's super cute. We got these little hamster figures in there, and you'll take a look at that in our in-person class. Now, I want you to think about this. Why do you have this feeling in your stomach when you go over the top of a roller coaster? If you've had this experience, you know you go over the top, you're accelerating downward, you have this weird feeling, and it feels like your stomach is rising up in your body. It's like your stomach is rising up. Why would you feel like that? And the answer is, it is. It is. If you are feeling like you're apparently weightless, and the people that are like free fall or something close to it are feeling apparently weightless, okay? It's as if you turned off the weight force. So your stomach, which is held in place by kind of like elastic tissues, okay, experiences an upward force from them. There's like a spring force. And there's also a downward weight force. If you turn off the weight force, your stomach will actually literally get pulled upward because the spring forces of the stretchy things holding your stomach in place are still acting, but it's as if you turned off weight. You didn't, but that's what it will feel like. And so your stomach really does rise up. Now let's do another force and motion problem, okay? Force and motion problem. And this one has a couple of pieces which I want to point out. So this is one about a person leaping from a platform diver, slows to a stop, 2.5 meters below the water surface. And so the question is, what is the force of the water to achieve this rapid stop? And you note You can't use the drag force equation for this force, because what the person is going to do in the water, they're going to change their orientation, thereby adjusting the drag force in order to achieve something like a relative constant force and a relative constant acceleration. And so we can't use the drag force equation. So people look at this problem and say, oh, I'm going to solve this using the drag force, and I've got a whole expression for the drag force, and it's complicated. Don't do that. Don't do that. We're just looking for the force of the water. We know there has to be a force of the water on a person. And if I've confused you and you're thinking like, oh my gosh, how do I solve this problem? We solve this problem the same way we solve every problem. But first, what we're going to do is this. We're going to take the problem and break it into two pieces, because there's clearly two parts. There's the falling through the air piece, and then there's the coming to rest, okay? So there's a falling piece, and there's a coming to rest piece. And if we draw a motion diagram for this, we can see this. The person starts at rest, and then they speed up as they move downward. And then at some point, they hit the surface of the water. Okay, they hit the surface of the water. And then subsequently, they slow down to a stop. So I would identify three important points in the motion. One important point in the motion is when the person starts, call that point 1. Point 2 is when the person hits the water. Point 3 is when the person comes to rest. And this first phase of the motion, that's free fall. Okay, because she's just falling through the air, and at the speed she's moving, we're going to ignore drag force. And then this is going to be a period of constant acceleration. Now, this is the kind of thing you could have done in Chapter 2. And in fact, you're just going to repeat that procedure. That stuff we learned in Chapter 2, we're going to keep doing for the rest of the course. So you break the motion into two pieces. We got a free fall piece. I got a motion with constant acceleration piece. And we can do some calculations. So let's set up a visual overview to do this, as we did right here. And I can look at my initial velocity. Well, my velocity at point 1 is equal to 0. Okay, my time 1 is equal to 0. My position 1 is equal to, and let's call it 10 meters, okay? At the second point, my V2, that's what we're looking for. What is T2? I don't know. What is Y2, the second position? Let's just call that 0 meters. That's the surface of the water. Then at point 3, I've got V3. She has come to rest again. T3, I don't know. And Y3, she's actually below the surface. I'm going to let that be negative 2.5 meters, okay? I'm going to let that be negative 2.5. because she ends up below the surface. And she ends up overall 12.5 meters below where she started. Started at 10 meters, finishes at negative 2.5. That's a total fall of 12.5 meters. And with this information in hand, I can use the techniques in Chapter 2 to calculate how fast she's moving when she hits the water. And 2, I can calculate what is her acceleration as she is coming to rest. And you can use the equations of Chapter 2 to do that. And you can use the one that doesn't use time. Like basically I don't know any times. I don't know this time. I don't know that time. So I can use the one that says like VF squared is equal to VI squared plus 2 times A times delta Y. Because in the first case, I know the acceleration. And in the second case, I'm looking for it. So that's the relationship we want to use. And if we do that, we get these values. How fast is she moving when she reaches the water? 14 meters per second. What is her acceleration as she comes to rest? 39 meters per second squared. And I'm just going to pause to do a quick assessment along the way. We saw a situation with the dolphin where the dolphin left the water at about 12 meters per second and made it to a height of about 7 meters. Okay, she starts at a height of 10 meters, and so we're going to expect her to hit the water at a speed slightly greater than 12 meters per second, and 14 is slightly greater than 12, and so that works out well. The other thing is she comes to rest with an acceleration of 39 meters per second squared. That's about 4 Gs. And I've said that 4 Gs is about the limit of what people can do comfortably, and we don't want to damage people when they're diving, so that number makes sense. So my assessment along the way, and I encourage you to assess everything you're doing as you're doing it, is everything is hunky-dory. And now this is the place where we're going to start doing the real force and motion analysis. And we're asked to do the things we're always asked to do: 1, motion diagram; 2, free body diagram. We did the kinematic stuff, we did the chapter 2 stuff, now we're ready for the chapter 4 and 5 stuff. So for the motion diagram, she's moving downward, but her speed is slowing. So the velocity vectors are getting shorter. Net result, we have an acceleration which points upward. If the acceleration points upward, that tells me the net force points upward. And if the net force points upward, that tells me that the upward force must be bigger than a downward force. Well, the downward force is just the weight, and the upward force, the thing that is bringing her to rest, is just the force of the water, okay? And so that's our motion diagram, and that is our free body diagram. Now we brought some information forward. Remember, her acceleration is 39 meters per second squared, okay? But we can, given the free body diagram that we've drawn, okay, we have an upward force of the water, we have a downward weight force, we can write an equation for the net force, and the net force is just equal to the force in the direction, in the positive direction, which is the force of the water, minus the force in the negative direction, which is N. And I'm looking for the force of the water. Well, the force of the water is just equal to the net force, F net, plus W. Now, you might be tempted to look in the book and see if you can find an equation like that. And there are, but they're typically intermediate stages of problems. This is not something which is generally true. It is true in this case, okay? And to get there, you've got to do all this work. You can't just jump to the equation. Now, force of the water is equal to F net plus W, but check it out. I know what F net is because remember, F net, that's just equal to M times A. And I know what W is. W is just the weight force. That's just equal to M times G. I have everything in hand to be able to calculate what the force of the water is. And I end up with the force of the water is 2,400 newtons, and that's about 5 times her weight. And my assessment is, you're going to feel this, okay? You're going to feel this. You're going to say like, wow, I felt that water bring me to rest, but it is not going to damage you. 5 times your weight, you're going to notice it's big, but it's not hurty, okay? So my assessment is everything looks good. These are forces that a person can tolerate, but it's going to be dramatic, and I expect it to be dramatic. Now, next piece of the puzzle. Are we done talking about force and motion? Oh my gosh, no. We're going to talk about more force and motion problems, and look at how excited some of us are to do this, and that's what we're going to do in the next set of slides.